Hello and welcome to the Daily Space for Tuesday, May 15 of 2018. I am Dr. Andreas Plazas and I am sitting in for Dr. Pamela Gay, who once again has failed to time zone and she needed to be at two places at once. So I'm here today again. As always, we are going to bring you a roundup of today's news from space and astronomy. And for today, we're going to bring you stories about galaxy formation, the Rosetta mission, and we also have even a story in which we ask, do we need a brain to develop intelligent life? So let's see. Okay, our first story is about the rotation of the most massive galaxies in the universe. So, a science team led by Dr. Davor Krajinovich from the Leibniz Institute of Astrophysics in Potsdam used a sample of bright galaxies up to a distance of 800 million light years away to study the largest and more massive galaxies in the universe. So these galaxies, they live in galaxy clusters. The most massive of them are about 100 times the mass of the Milky Way, and they are old galaxies that they don't have a lot of gas and they do not form stars anymore. So why do we care? Because if we study the movements, the stellar movements of these galaxies, we this is a very powerful way of learning about the internal structures of galaxies. This is going to tell us about the three-dimensional shape of the galaxy and even the gravitational potential of the galaxy, and even is going to tell us hopefully about how the galaxy formed. So in order to perform this measurement, they use what we call an integral field unit. So they use an instrument called MUSE, and it's part of the European Southern Observatory. This is located in a telescope called the Very Large Telescope. As you guys know, we are very original in astronomy to name our telescopes. So this is the Very Large Telescope is located in Cerro Paranal in Chile. And the cool thing with this type of integral field units is that you can get an image of each pixel of a galaxy, and at the same time you can get a spectrum of that same pixel. So how do we tie this to the story here? So these researchers actually were able to measure the average velocity of stars in a particular region of these galaxies. And then if you can look at the spectrum, you can see how the spectrum is either shifted a little bit towards the red part of light or towards the blue part of light. And this is going to tell us about the velocity of of the stars due to what is called the Doppler shift. And this is going to tell us about how the galaxy rotates. So the interesting thing is that the majority of galaxies, for example, the ones that are similar to our Milky Way, that are not as massive as these galaxies, they show very regular stellar motions. What does that mean? That the rotation is well defined. Our Milky Way is a disk. It has a well-defined rotation, and the rotation is about the short axis of the galaxy. In this study, however, these researchers found that these massive galaxies they rotate preferentially along the long axis. So it's more like a rugby ball or like an American football ball. So, well, this is what does it mean? How do they tie this to the formation of the galaxy? These measurements actually tells us about how the galaxy formed, because numerical simulations they indicate that the rotation along the long axis is telling us that that this galaxy came to be as a merger of two massive galaxies with similar size and mass, and that they were mainly on sort of a head-on collision trajectory in space. So after that, then we're gonna have stellar motions that become very complex. They're not like in the Milky Way that are very well defined, and this is an example of what we call a hierarchical galaxy formation scenario. So, in general, the formation of galaxies is not very well understood, it's not fully understood. However, astronomers have identified three processes that are involved in formation of galaxies. One of them is what we call the primordial collapse. It's just the collapse of individual gas early in the history of the universe after the Big Bang. Then we have what we call the hierarchical clustering, in which the formation of galaxies comes from you start with the smaller galaxies that also merge into bigger ones. And in the end, we also have something that we call secular evolution. And what does that mean? It means that the formation is a result of internal processes, such as in the action of a spiral arms or bars. For example, we think that a galaxy like the Milky Way formed mainly due to secular evolution. There's a lot of stars that are still being formed in the Milky Way. And then we believe that this is the main mechanism in a galaxy such as the Milky Way. So we have these three mechanisms, but we don't know. The real question is, what is the importance of each one of them in the process of galaxy formation? And then to wrap up, to finalize, then this study that we're talking about today is telling us that these massive galaxies, their main mechanism, the way that they rotate is telling us that their main mechanism for where they formed is the merging of the hierarchical cluster mechanism. So this is very cool, and that's what we think this is very interesting. So now we're going to talk about our second news of the days, and this has to do with the Rosetta mission, as many of you have remembered. So the Rosetta mission, it was launched on the 2nd of March of 2004, and then from August of 2014 to September of 2016, it orbited a particular comet in our solar system that came from the Kuiper belt into the inner solar system. This comet is called 67P slash Churyumov-Gerasimenko. So for short, we're just going to call it 60CP. And those two names are the names of the two Soviet astronomers who discovered this comet in 1969. So more than 70,000 images were taken by the scientific camera called OSIRIS and on board of Rosetta. And the researchers for this team have now investigated this data, have reanalyzed this data, and they have investigated the activity that occurs regularly every morning. What does that mean? In the region where you find the sunlight falling on the comet, and then you find the shade, like for example when you look at the moon. So that line is actually called, it has a cool name, it's called the Terminator line. Well, this is a special point because actually this is going to tell us, we already can tell that the temperature is going to be different. So we expect to find some differences, some unusual activity in this particular region or at this moment of the day when the sun rises. So the researchers, they say that when the sun rises over a part of the comet, the surface along this terminator line becomes almost instantaneously active. So they report that they see jets of gas and dust, and they find that every morning in the same place, then you find these particular jets that are actually also found when you do numerical simulations. And for those of you that are watching the screen right now, we have a picture on one side on the left of an actual image from Rosetta, but on the other side we find simulations, like the results of numerical models that are able to reproduce this type of jets. So why do we have these jets? So the researchers say that the responsible mainly for this morning activity is the frost, which forms at night on the cold comet surface, and then as soon as the sun's rays touch it, well, the frost begins to evaporate. And why is this important? Why are these jets important? For scientists, these jets are the key to what they call the cometary activity, because then this is telling us which processes on the surface are involved in the formation of these jets, what do they reveal about the nature and composition of the comet, and hence about the origin of the comet, and therefore about the origin of the solar system. So as I mentioned earlier, this is an object that is coming from the outskirts of the solar system that is called the Kuiper belt, and is probably telling us about the early solar system. So part of the reason why we are very interested in studying comets. And then to finalize, they mention a curious fact that actually, why do we have jets? Like, why doesn't the frost just spread in a more uniform way? They actually point this as a consequence of the geometry of the comet itself. As you can see in the picture, if you can Google it, this comet has the shape of like a dumbbell. Like you have two main lobes that are connected by you can call a neck, and the jets are found in the neck. So the shape of this region is mainly responsible for the shape of these jets. The pits and other concave structures are virtually concentrating the gas and the dust emissions in a similar way like a lens, an optical lens concentrates light or focuses light. If we had an spherical or even a potato-shaped comet, these structures might not be as prominent, and the gas and the dust would be much more distributed. So actually, in this research, the scientists point out that usually it is better to have a geometrical object when you're studying the objects in the solar system, but in this case, the topology and the geometry of the comet has worked in their favor. It has been what they call a blessing instead of a usual curse. So, yes, that's our second story of the day. And then, as I mentioned earlier, we're gonna finalize with a particular story about brainless forms of life. And we're gonna talk about intelligence. So, in this article that I'm going to talk about, this is highlight. So we ask ourselves the questions: how do we define intelligent life? Like, does an organism need to have a complex brain in order to develop intelligence? So one definition of intelligent life that we can have, and that people, some researchers have, is that intelligent life has to have self-awareness, should be able to use tools to modify the environment, and maybe to use a language. But however, this article highlights some brainless forms of life that can perform tasks as complex as counting, anticipating future events, and even optimizing or finding the shortest path between 2 points. So, depending on your definition, um, we can say that these creatures are intelligent. And why is this important for us? Because well, as you know, we one of the questions that we want to answer is there life out there in the universe outside of the Earth? So the first thing that we need to decide is, how do we define life? That's a whole complex problem right there. What do we call life? And then on top of that, we need to find out what do we call intelligent life, right? So in this article, they give two main examples. One of them is slime molds, which are actually they're like soil-dwelling amoeba. They're brainless and they're single-celled organisms, and they often contain multiple nuclei that can spread out in several square feet. So the article points out that these molds, they actually could find the shortest path to food, building a series of tube-like structures that circulate nutrients and chemical signals. And one of the cool things that is mentioned is like, if you arrange food in one of the experiments that researchers have done, if you arrange food at points that look like the Tokyo train station, for example, then you start to notice that the slime molds are going to reproduce trails that resemble the actual rail network. What does this mean? That is, it's telling us that the amoeba are actually trying to find the shortest path between 2 points, which is an optimization problem. They also mentioned that this type of organisms have been able or identified, they have been identified to solve mazes or to act as if repeated past events will continue into the future. They have even learned to tolerate substances that they avoided at first. And then they provide a second example um, of jellyfish, actually, of jellyfish showing a sleep-like behavior. And this was actually reported in an article from last year, and it was the first time that this behavior was seen in an animal without a central nervous system. So this is also telling us that an early version of a sleep mechanism was present in the common ancestors of jellyfish and other animals about 600 million years ago or so. So, well, let's remember that sleep is fundamental in other animals such as ourselves. Like, it's helpful to heal the nervous system, it strengthens the memory, it helps to conserve energy. So, in addition of this article of being cool in and by itself, we wanted to talk about this because um, when we're doing a space exploration, we want to ask ourselves, how do we identify life when we see it? And after that, how do we identify intelligent life when we see it? And then even going beyond, we'll have to ask moral questions like, what do we do if we find what we decide is intelligent life in another planet? And let's say we have the technology to be there. Like, do we have the right to go there, or what do we do? So these types of examples in our own planet makes us think about what we can find out there, of course. And for those of you that were listening to me last week or the other day, I was saying, of course, I mentioned that we start by considering life that we know, the examples that we have of the Earth. But of course, we have to consider the option that there's something we haven't even come to imagine. But for the moment, the research that we do to find life in other parts of the solar system, they try to, or the solar system or the universe, try to identify biosignatures such as oxygen, nitrogen, or signatures that are consistent with life as we know it, or even signatures from advanced civilizations that could have developed, for example, electromagnetic communication. But every time you read these articles, then of course you have to know that this is based on a lot of assumptions that we're assuming that the other civilizations are actually similar to us, and they have actually developed means of communication similar to the ones that we have. And to me, this points a little bit to that anthropomorphism that we have. Like even since the beginning um, of when we as humans started to write stories about what life would look like, we started to picture other forms or life forms as looking as us, but that doesn't necessarily have to be the case, right? They don't necessarily have the green little men don't necessarily have to have two arms or two legs or whatever. And there's also the option that there's nothing else, right? I mean, so far we don't have any evidence, and we, for the moment, the only thing that we have to do is to keep speculating and doing more experiments until we find empirical evidence for life beyond the Earth. So yeah, with that comment and that final opinion. So yeah, well, that has been the program for today. Thank you very much for watching. This has been the Daily Space, a production of CosmoQuest, created by the Astronomical Society of the Pacific. And our goal is to put science in your intelligent brain. And well, if you like the show, please give us a follow. Follow us are free. If you want to sustain our efforts, please consider subscribing. Every bit also helps. So now I'm gonna hang out a little bit and maybe um, answer some questions if I know the answers. And if not, we'll see. You'll hear me rambling about what I think about your questions. Hold on. There you go. Hello. Do you guys have any questions or any comments? Thank you guys. Thank you. I'm saying hi to Guido V, Paranor 001. um, Somebody points out that my face has been cut off. Sorry for that. I'm trying to figure out how to locate myself in a space. Some lack of intelligence right there. Sorry, next time I'll try to look more into the camera. And yes, and after this, of course, I'm gonna look at for some questions. But of course, after this, we're going to have Dr. Matthew. Next up on this channel, we will have Dr. Matthew Richardson, and he's gonna bring us some astro office hours. But before that, I wanted to see my. Somebody asked what is the subject of my dissertation. If you Google my full name, you will find that I work on gravitational lensing. Systematic errors in weak gravitational lensing, to find out more about dark energy and stuff like that. And so, isn't finding life of all sorts also a scale problem? How small could intelligent life possible get? Yes, absolutely. That's a great question. And this is an example of the subject of today, that we're finding these amoeba, these unicellular forms that are smaller than us, and we're trying to figure out if these behaviors can be defined as intelligent behaviors, right? Well, some people might say, well, the fact that these things find the shortest path between 2 points, that doesn't mean that they are intelligent. It just means that they're trying to conserve energy, and that's something that nature does all over time. But then, exactly, and this question is very tied in hand with what we call life, right? What's the smallest thing that we call life? I'm not a biologist, right? But do we call a virus something that is alive? Um, so yeah, it's a problem of scale. And then on the other side of, I'm speculating a little bit here. On the other side of the spectrum, if we have like giant forms of life, are we gonna have like intelligent beings that are like orders of magnitudes larger than us? Or maybe there are some fundamental limits given by the laws of physics, like the mechanics, like the size of the brain cannot develop as large, or the gravity of the planet is too large that it doesn't allow these things to grow up. And so yeah. um, Somebody is asking about what I do. What is the boundary between gravitational lensing and gravitational microlensing? All right, I can talk a little bit about that. In general, it's just they're just convenient labels. There's only one thing, which is called gravitational lensing. It's a consequence of the distortion of a space-time by any distribution of mass. So you have the bending of light due to this distortion of a space-time. And then sometimes that distortion is very, very large, and you can see galaxies get super elongated, and you can see them by eye. And then some other times the distortion is so tiny that you cannot even tell. And then we just, in these different regimes, you cannot tell with just one galaxy. You need a statistical ensemble to figure out that there's some effect. And long story short is like they're just names. The effect of gravitational lensing is always there wherever you have a mass distribution that is distorting a space-time. It's just that for convenience, sometimes you call it a strong lensing, sometimes you call it weak lensing, sometimes you call it micro lensing. And depending on that, depending on the strength of your signal, then you use a different mathematical approach. just to finalize, for example, in a strong lensing, you're gonna have, if you Google a strong lensing Hubble Space Telescope, you're gonna see multiple images of a background galaxies, and that's telling you that the equations have multiple solutions. But if you Google weak lensing, you're gonna have just a small, tiny distortion of one galaxy, and that's telling us that in this case the equations only have one solution. So the way that you use the math there is just different. In one case, you need to solve a nonlinear equation. In the other case, you need to solve a linear equation. So, yes. So, so now we started talking about gravitational lensing. Maybe next time we find some news about that, I can tell you more about it. Um, So I think I'm taking up some time, and maybe I should just hand this over to Dr. Matthew Richardson. So I'm gonna wrap up, and then, well, once again, guys, this has been the Daily Space. It's a production of CosmoQuest, created by the Astronomical Society of the Pacific. Um, Give us a follow if you like this show. The follows are free, and if you want to sustain our efforts, please consider subscribing. And the next up on this channel will be Dr. Matthew Richardson with astronomy office hours. I've seen some of his streams, and it's pretty cool because he actually solves all these equations. For example, the other day he was solving general relativity and how you can get from general relativity to Newtonian mechanics. And now that we were talking about gravitational lensing, that's a consequence of general relativity, for example. And okay, the Daily Space will be back tomorrow, and every weekday at 1 p.m. Eastern, 10 a.m. Pacific, 6 p.m. London. And tune in tomorrow. Pamela will be back, so you'll be happy to hear that. And yes, come back tomorrow to see what is new in space and astronomy. Okay, guys. Ciao.